Gum arabic was defined in Thorpe's Dictionary of Applied Organic Chemistry as the gummy exudates from acacia trees grown in hot, dry climates. Gum arabic is used to thicken foodstuffs and also pharmaceuticals, and before the bacterial dextrans were used, gum arabic was used as a blood plasma extender. Blood plasma extenders are used to treat patients who are in shock after losing a good deal of blood. According to Thorpe, the most esteemed variety of gum arabic of commerce is a gum obtained from Acacia senegal, which grows in the Kordofan province of Sudan in North Africa. So when we talk about gum arabic, we really mean Acacia senegal gum, and sometimes called Kordofan gum. Sullivan and others were interested in the chemistry of gum arabic before 1900, but very little progress was made. Then in 1929, a most unusual paper appeared from Heidelberger, Goebel and Avery, who were working in the Rockefeller Institute in New York. They reported that they'd hydrolyzed gum arabic for a short time with mineral acid, and that an aqueous solution of the degraded gum gave strong reactions with both type 2 and type 3 pneumococcal antisera. Heidelberger's work excited renewed interest in the chemistry of gum arabic. During the early 1930s, Nobel laureate Sir Norman Howard and Edmund Hirst, who were working in the chemistry department of the University of Birmingham, England, became interested in the chemistry of gum arabic. A few years later, Fred Smith joined them, and then significant advances were made. The going was by no means easy, and 20 years later I heard Gerald Aspinall in Edinburgh state that his papers published in the Journal of the London Chemistry Society in 1939 and 1940, Fred Smith described the very finest experimental work ever carried out in organic chemistry, of course up to that time. Even so, I think Gerald Aspinall's statement was a wee bit exaggerated when we think of some of the things that Emil Fischer, Hans Fischer and Reichstein managed to do. But Fred Smith's work was very good indeed. I once remarked to late Professor Fred Smith that it was amazing he did work of that quality before paper chromatography was used in carbohydrate chemistry. All he said was it was very difficult. So now there's a formula of the gum arabic macromolecule as given by Aspinall, Hirst and Nicholson in a paper in the Journal of the London Chemistry Society in 1959. That formula was based on the results of the British school in 1930s and 1940s, on results which Fred Smith and his collaborators obtained in Minnesota in the 1950s, and of course the few results which were obtained in the 1800s and early 1900s. The story I heard was this. In 1942, the British government sent Fred Smith and some other British scientists to Canada to see if they could make an atom bomb. The British scientists collaborated with Americans who were working on the Manhattan Project, and a few atom bombs were made. While he was in Canada, Fred Smith met and married an American woman, and after the Second World War, he became a professor at a university in Minnesota. From the previous formula, it can now be seen that P is D-galactose in the pyranose or six-membered ring form. DGPA equals D-glucuronic acid in the pyranose or six-membered form. Now R can be L-rhamnose in the pyranose form, or it can be L-arabinose in the furanose or five-membered ring form, or it can be a disaccharide where D-galactose is linked to L-arabinose by a 1,3 link, and in the molecule, the arabinose is in the furanose form. Some people may be surprised to see that the individual monosaccharides can be either in the D-stereochemical form or in the L-stereochemical form. In fact, the D and L stereoisomers of the same monosaccharide can occur in some polysaccharides. When she was working in the chemistry department of the University of Cape Town in 1957, Mavis van Holt showed that D-galactose and L-galactose occur together in one of the seaweed polysaccharides. In their paper in the Journal of the London Chemical Society, Mavis van Holt and John Nunn stated that they'd obtained pure D-galactose and pure L-galactose from the D-L mixture using fractional crystallization. So it's understandable that Mavis van Holt had the reputation of being a top-flight experimentalist. Now, for the benefit of people who are unfamiliar with this type of sugar shorthand, I'll briefly describe what it's all about. If we were to line up two of the molecules of galactose shown and remove the elements of water from the molecule on C1 on the left with a hydroxyl group at C3 on the right and link up the bonds, we'll get a disaccharide where the two D-galactose units are linked by a 1,3-glycosidic bond. Add another galactose to the right and do the same thing. We'll have a trisaccharide with two 1,3-glycosidic bonds. Another one, we'll have a tetrasaccharide with three 1,3-glycosidic bonds. And in this way, we can build up a long chain, which is the main chain of the gum arabic macromolecule. Now, if we put another galactose unit above the main chain and remove the elements of water from the molecule above the chain at C1 with the OH group in the main chain at C6, you'd get a galactose in the branch, and the branch would then be linked to the main chain by a 1,6-glycosidic bond. If we can have branches to the main chain, there's no reason why we shouldn't have branches to the branches, and in gum arabic you do, and these branches, denoted by R in the formula, are the residues L-rhabdopyranose, L-arabofuranose, and the galactopyranose, galactose-arabinose disaccharide. Where these residues are linked to galactose, they're linked by 1,3-glycosidic bonds, but where they link to glucuronic acid, they're linked by 1,4-glycosidic bond. A solution of crude gum arabic would be pH 7. When Fred Smith was working, it was known that the counter ions were potassium, calcium and magnesium. It's now known that there are much smaller quantities of sodium ions and ions of the transition elements, copper, iron and manganese. Fred Smith poured a solution of crude gum arabic acidified with HCl into 5 volumes of ethanol, and the arabic acid precipitated. If you make up a solution of 5% solution of arabic acid, the pH will be about 2. And if that solution is heated on a boiling water bath, you get slow autohydrolysis. After 5 hours, you should be able to pick up the L-arabinose, the L-rhamnose, and the galactose-arabinose disaccharide. After 15 hours, you should pick up galactose, and in order to break the link between the glucuronic acid and the galactose, the solution has to be heated in molar sulfuric acid for 24 hours at 100 degrees centigrade. So the color coding on the slide shows the relative strength of the glycosidic bonds. when you're carrying out acid hydrolysis. The most labile bonds are the ones in green, the most acid resistant in red, and those in between in orange. And now I'd like to point out some unsolved structural features. What are the exact positions of the acid labile residues, denoted by R in this formula, a dash from now on, in the periphery of the gum? For example, what is the acid labile residue in the box shown? Is it L-arabinose, or is it L-rhamnose, or is it the galactopyridose L-arabinose disaccharide? In a review article, Hurst made R' L-arabinose. That was really just a suggestion.